Welcome back. In this lecture, we will look at energy balance via control volume. In the previous lecture, we had looked at energy balance for a closed system. So this involved connecting conservation of energy to heat transfer and work transfer. We had discussed uh, quantities like enthalpy and specific heat, defined them and uh, use them in the context of first law of thermodynamics. Typically, we illustrated them how to implement and compute these values, implement first law of thermodynamics and compute these values in special situation, and we illustrated the computation procedure. However, most of the engineering systems are not closed system. For example, this is part of an airplane, and this is a heat exchanger where fluids come in and go out at a different temperature, and heat is transferred to heat up this fluid. And here we are showing a nozzle and a diffuser. And all these things are flowing systems. Okay, there are things that they're not closed systems. There are incoming mass of fluid and outgoing mass of fluid. So how do we implement first law of thermodynamics to these systems is the goal of this and the next lecture. Although this is not a course on fluid mechanics, you should become familiar with how to implement mass balances in flowing systems. Supposing you should know how to calculate the average velocity given a velocity profile, for example, in a pipe and so on. So once this average velocity is known, with the cross-sectional area, you can also get the volumetric flow for the system. From there, given the density of the system, you can also get to the mass flow rate of the system. So you should know how to think about the relating to the changes, relating how to implement the conservation of mass for our system of arbitrary geometry. The most general expression is provided here. So you can relate to quantities that are varying in the control volume to the quantities that are flowing across the control surface, right? So this is comes from elementary laws of vector calculus. You should know how to implement this for systems. At least you should be familiar, although this is dealt with in much greater detail in courses in fluid mechanics. For example, the other course on ESO, fluid mechanics and rate processes, these things are done. But you've also seen this in your electricity and magnetism course in Griffiths and so on. Okay, so these are all very similar. I mean, this is an implementation of a mathematical theorem for a variety of situations. We can also think about the mass flow. We can relate. We're implementing this. This is the term here. These two come from implementing this term, right? It tells you the incoming mass flow rate, outgoing mass flow rate. So the change in mass per unit time in the control volume can be related to incoming mass flow rate and the outgoing mass flow rate. Okay, so most fluids which we encounter in engineering systems are incompressible. That means there's no variation in density. So for this, this equations can be further simplified because density is a constant that is not that doesn't change. So we can also implement in this term would not be changing. Therefore, and if the density remains a constant, the volumetric flow rate of incoming fluid is the same as the volumetric flow rate of outgoing fluid. Okay, so these two happen to be the same. While we have laws for conservation of mass, there is no real law for conservation of volume. For example, here, when you consider air compressor, there is, if you implement a conservation of mass, you can see that the mass flow at steady state, the incoming mass per unit time is the same as the outgoing mass per unit time. Okay. However, the volumetric flow rate, incoming volumetric flow rate, is not the same as the outgoing volumetric flow rate because the temperature here can be different from the temperature here, and the density can also be different. Okay, so there's no conservation of volume, however, there's conservation of mass. Okay, so all right. So having done all these things, we would, in the next lecture, we would implement this mass balance and how to incorporate the equations that we obtain from implementing mass balance to overall energy balance. That will be the agenda for the next lecture. Thank you.